I'm from Huawei, and today I'm going to talk about enhancing remote healthiness attestation for constrained IoT devices. IoT devices is really vulnerable and is still a lot of attacks are targeting and IoT devices. And IoT devices is usually used to launching DDoS attacks. For example, the Maria attacks in 2016, the peak value, traffic value is about to 1.7 terabytes per second. And it's easy for attackers to control these IoT devices to launch a huge traffic to attack. The reason behind why IoT devices are easily to be hacked and they are constrained resources is because of the market shaping. Due to the cost consideration, a lot of IoT devices are resource constrained. So that means they are unaffordable for a lot of security mechanisms, just as the smartphones. So hackers are like to hack these devices and using their the limitation of the security mechanism to put the bugs into the IoT devices.
Excuse me if I interrupt you. Can you please show a figure of something that represents your poster so that we can figure out what to ask? Because we're not supposed to listen to presentation.
Sorry. You mean I should present the paper, or
No.
should I present the slides?
No, you should, like in a poster session, in a regular poster session, you should show something that people will be stopping by, will arrive, stop by, and ask about. But if you give a presentation, if you give a presentation like this, we risk to have nobody. Basically, nobody will have the option to jump from one track to another and see multiple posters.
Okay, I got your point, and but the only thing I prepared is the slides.
But don't you have any representative figure on top of which we can ask something? So I'm curious to know.
Okay.
What was the motivation of your work? But if I don't know what you did at a glance, how can I ask?
Okay, maybe I can switch to the detail. This slide shows the detail of the design and so I think this is a summary for what we did, and but yeah, it's not the framework of the whole paper.
Doesn't matter. I mean, it's important we discuss what are the things that you are doing. Not, I mean, we can read what you wrote in the standard abstract, but now I want to understand what kind of research you are tackling. What are you focusing on? It's security rather than system engineering. How will you define what you are doing?
Okay, I'll start from the slides. What we are doing is about improvement for the already exist mechanism. It's called DAS, and what we did is to provide a proposal. It's called DAS Plus, and we improve the DAS in 3 directions. And the main consideration for this work is to improve DAS by fixing the possibility of replay attack and make it be replay attack resilient. And we start from here. Sorry.
So where you have three levels here of security or whatever. No, one is security, lightweight, accuracy. What are these? Are they the feature of a software that you developed, or what?
It's a parallel improvement.
Okay.
The main contribution is about the security, but we still want to make this mechanism be lightweight. So we have another considerations, but the main purpose of this work is about security.
Okay, but okay, please go ahead. Can you tell me about software implementation and challenges you have focused on?
Okay, sure. Let me just briefly go through why the DAS is replay attack is able to be replay attacked. This slide gives some brief detail why the IoT device is easy to be attacked. It's just because they are like a lot of devices are lack of the hardware security protection. So every credential stored on these devices are easy to be the credential are easy to be stolen. So what we did is to insert a seed when the process of the whole dice process, and because we have the seed on the both side, I mean the device side and the cloud side. So every time the device booted, and there will be a brandly new credentials, and the cloud side will get this change. So every time if the hackers want to steal credentials, the attacking window is extremely small, and due to the seed here, we use a sequence counter in the DAS process engine, and that makes the change of the whole output of the credential. So that's the main change we did in this work.
Yeah. Okay. Thanks. And what do you think you will do with this system? Are you planning for a follow-up of this work that somehow will end up in a paper or maybe a patent? What?
Sorry, I haven't followed your question.
What's the final target that you have? Are you targeting a full conference publication rather than a patent out of this?
We are trying. We are making this put into use in our company products, especially for the extremely lightweight, constrained resources IoT devices, and we are making it into the product line and make it to put it into use.
Nice. But is this something that can reach the market soon, or what? I'm curious about this IoT devices, because so far, apart for cameras and a few more things, I don't see many secure IoT devices that are sold. So what kind of IoT devices do you have in mind?
Especially for that sensors.
Mm-hmm. Okay.
Yes, especially for that, the extreme low power and extremely constrained resources for a special kind of IoT devices.
I see. Okay, thank you very much. I will have to jump to another poster presentation because I want to have an idea of what is going on in the other tracks. So since I was one of the organizers, but thank you very much, and I invite everybody to ask questions and to interact with the presenter now. Okay.
Okay.
I may be back later. Talk to you.
Hi, Andreas. I think it's your turn already to show your poster and try to explain a bit.
Hello?
Hello? Did you hear
Hi.
me?
Yes, yes, I could
Okay,
hear you.
so let me remove. So, how can you stop sharing
Sure.
your? I don't. Yeah. So now I think you can start sharing, Andreas.
Okay.
Thank you. I hope there is someone asking now. Let's see. Oh, nice poster.
Can you see something? Yes, I
Yes, we
guess
can
so.
see the poster.
Okay. I guess I should wait, or should I
Maybe
start
you can
explaining?
introduce yourself and talk a bit about your group. Maybe what are you doing, and maybe give a brief explanation of what you've done, so people have
Okay.
an idea and can ask.
Okay.
Thank you.
So hello and welcome to my poster presentation. My name is Andreas Bäuml, and I'm working for the CMO lab at TU Darmstadt, which is a we are doing research in secure mobile systems. This work was a joint work with National Instruments and with Clemens Felber and Dr. Walter Nitzold. And yeah, my work is an experimental study of multi-radio access technology systems, and it was conducted last year in 2019. So, okay, so if you have any questions, just interrupt me so we can talk about it. So our objective was during the course of the project to define evaluation scenarios where we are able to evaluate those multi-radio access technology systems, then implement required logic and features, and have the experimental analysis of multi-radio access technology communication. But what did we have from the beginning? So we had a full a complete network with software-defined radios that were running either Wi-Fi or LTE code that were connected to a core network, and the core network was a NS3 network, and the MAC layer and physical layer was both a LabVIEW code running on software-defined radios. And we also had a traffic sync, which was also a software-defined radio, and it was also connected to a computer running NS3. So we had a full network that was capable of sending and receiving data. And in this network, we made a couple of measurements like throughput and latency and jitter and CSI information and stuff like that. And from the hardware setup, you can see on the right side here, you can see the software-defined radios here. The UE was connected to a PXI station that was connected to a computer running the upper layer code, and the software-defined radios were running the MAC layer and physical layer code. And also you can see like the core network where we had a Wi-Fi access point and then LTE base station. And we were able to route the traffic from a traffic generator through a controller that would control if we wanted to use either the Wi-Fi link to the traffic sync or the LTE link to the traffic sync. And there are two different protocols that can handle that in that test bed, which was LWA and LWIP, which the difference between those two is just that they operate on a different level, on a different layer of the network stack. So what we did was, you can see on the right side here, the experimental analysis. So we had, defined a couple of evaluation scenarios, like I said, and we wanted to see how the different links behave to interferer, and you can see here an interferer. And for LTE, we wanted to simulate basically a network occupation. We did that by not using a interferer, but by lowering the modulation coding scheme and the physical resource block allocation for the UE. And then we set up the experiment, set up the traffic generator that was sending TCP data to the UE, and then we separated the experiment of 45 seconds into 4 phases. And with at each phase, we lowered the MCS and the PRB, and and you can see the outcome here. And we observed that that the link was in phase 4, where we lowered the MCS and PRB to the lowest value that was possible, that it was still possible to transmit data, even though at a very low rate. For Wi-Fi, you can see here at this in green, again, the 4 phases, and for phase 1 with no interferer, and then we gradually turned on the interferer. And interestingly, Wi-Fi broke down completely in phase 4. You can see, like, for a couple of seconds, we did have no throughput at all. And also, that is not shown here in those graphs. The delay spiked here a lot in the Wi-Fi in this Wi-Fi experiment. So what we did then, based on those experiments, we implemented a couple of things at the testbed. The code for the testbed is available here, by the way. So we implemented a couple of things, like packet merging at the UE, which was not available at the time. And we also implemented a feedback mechanism for LTE and Wi-Fi latency and throughput measured at the UE. And we did that by using the CQI feedback mechanism. So as you can see here, we measured throughput, latency, and jitter here at the traffic sink, and we wanted to have a mechanism to feed it back to the SDR/SDN controller here. So we did that by using CQI feedback mechanism. And also, based on the outcome of the experiments that I just introduced here, we implemented a very simplistic threshold-based multi-rate scheduler that was running right here on the network on the SDR controller here. And well, at a very high abstraction layer, this was the code that we used for the scheduler. So basically, if we were running Wi-Fi and the jitter was above a certain threshold, or the latency or the throughput was below a certain threshold, we switched to LTE and waited 2 seconds, and the same for Wi-Fi, basically. And then we repeated the experiment. So we realized here that in the testbed, the Wi-Fi was the more reliable link at the beginning. So we set it up to use Wi-Fi at the beginning. And then after 10 seconds here, okay, let me zoom in. After 10 seconds here, we introduced the interferer, and we turned it on to maximum. And you can see that we immediately switch to LTE once the Wi-Fi link breaks down. And well, we do have a very high spike in LTE delay because we spike in throughput as well. But then the delay goes down again. We switch one more time here to Wi-Fi, which doesn't really work. So this was, you can see, like, there was no throughput in this in those 3 seconds or 4 seconds. But then we switched back to LTE, and the link worked until we turned off the interferer here and had the Wi-Fi and LTE link work perfectly again. In terms of numbers, you can see the observed throughput, latency, and jitter for the different experiments here. So in Wi-Fi only, we had a throughput of, well, about 1.3 megabyte per second, and and LTE was a little bit higher, almost 2. But with the multi-red scheduling algorithm, we were able to achieve a higher throughput because we switched the link once it was degraded. And the same for the delay. And most important here is the jitter. Well, the Wi-Fi link broke down completely. That's why we do have a very high jitter. And if I remember correctly, we had like a 99.9% or 99.7% of decrease of jitter here compared of the from the multi-red algorithm to Wi-Fi only. So this was a significant increase in terms of performance, just with this very simplistic threshold-based algorithm. So if you have any questions, feel free to ask. Yeah.
Hello, Andreas.
Yes. Hello.
Hi. This is Emir Halipovich from AT&T Research.
Mm-hmm.
So you did this using the software-defined radios, and what are the UEs? Real UEs or?
No,
what
I
are
didn't. I couldn't understand the question.
You're using software-defined radios for the base station,
Yes.
and UEs are the user devices are what? Also software-defined?
Also software-defined radios. Yes, you can see here.
Right.
Those are 2 software-defined radios, which was our UE.
So you're showing the success in quick switching.
Yes.
Issues are detected on one link. How is this different from taking a real device, enabling smart switch, such as available on Android, and testing the setup with or without smart switch?
So unfortunately, our setup that we were provided, this doesn't work with a commercial off-the-shelf UE, so we weren't able to test that. What we did test was were the 2 different protocols, like LWA and LWIP, and well, I can also show you another one slide of the presentation that I gave. So different. So I'm not aware how the smart switch that you just talked about works, but what we did was we didn't. So we had this whole network in NS3, and what we did was we routed the traffic for Wi-Fi, not directly through the mobile network gateway node and then to the through the Wi-Fi node, but we routed it through the SGW, PGW node, and then the ENOP node, and then through this additional interface here, which is the LWA, LWIP interface, and then to the Wi-Fi access point. So I'm not sure. I'm not aware of the specifics of this smart switch, but I guess this is a little bit different. It's a different layer that we switch.
Okay, but in order for this to become sort of a successful solution, what is the problem you're solving? What is the when there is here's really the basis for my question is when there is something similar out there in production, it would be important to evaluate your solution against that, compare and contrast to it, to show either that it solves the same problem in a better way, or it actually solves a little different problem is also important. Because ultimately, I believe you want your solution to somehow be successful and seen as useful and accepted potentially in real life, which essentially means either in Android or iOS, somebody, either Apple or Google, have to pick it up, or a device manufacturer, a large one like Samsung or Huawei, or right, and implement their version of the probably Android OS. Ultimately,
Yes.
also end up in a non-smartphone devices, such as some home devices, potentially smart speakers and whatever. It doesn't really matter. I'm kind of lacking the context here for that. Like, how is this different from what they're doing right now, right? And if it's not different, how is this better?
Yes, that's that's absolutely a valid point that you're saying. So the next steps would be to compare this to the already existing solutions that you just have talked about. The cool thing here was that we had a testbed that was completely open source, so we were able to do the switching at layers that we wanted to, and see how it actually works, and where the delay comes from in the network and stuff like that. So we had a complete network that was completely based that we completely ran and that we completely operated, and that was basically the point in using the already existing Orca facilities. But yes, that's absolutely a valid point that we should compare this, or the outcome of this, to already existing solutions. But at the moment, as of right now, it's not possible with the existing testbed that we have.
Well, I understand that the testbeds would be completely different, right? This is a fully controlled, the entire end-to-end, including the infrastructure setup, whereas using real devices would be, is simply just a measurement of whatever you're given. But I think it would still be valuable, because ultimately your end result is the bottom right charts, right? How does throughput improve, and how does delay improve as well, right?
Yes.
That is also measurable using off-the-shelf devices. You take a few phones, connect them to whatever production LTE and Wi-Fi networks you have, turn on smart switch, turn it off. You could still measure throughput, achievable throughput, and impact on delay. you don't know what's going on inside the infrastructure, how packets are routed and what's going on. I give you that. Absolutely. You don't know it. It's a black box, but I think it's still useful. And I am intrigued with this solution. Like, I like these approaches because personally, I have experience where I like the switch and where I don't like it.
Mm-hmm.
So I don't know how people generally look at the, cellular versus Wi-Fi switching, but this is how I look at it.
Mm-hmm.
When I'm at home, okay, I could be on cellular only. So on my phone, Wi-Fi is turned off, right? Then I want to go out and walk the dog around the neighborhood, right? And when I do that, I basically want to start some podcast on my, and have my Bluetooth earphones and things like that. And I just started as I'm leaving the house, and everything is fine. The problem is when I have Wi-Fi at home, and I do that, as I depart from the house, the phone is losing the signal from Wi-Fi,
Mm-hmm.
right? And at some point, it's gonna become bad enough that whatever I'm listening through the network is gonna break. And the phone will eventually switch to cellular because it's out of range of Wi-Fi.
Right. Yes.
And that's where I think everybody would want a seamless transition, such that there is no failure in what's going on, whether it's a phone call, potentially a podcast, or whatever you're listening to through the network, Pandora, doesn't matter. And I think that problems do still happen. So this type of switch is a very useful thing. Ultimately, when you do the reverse and you're entering the Wi-Fi network, you're still connected to cellular. The decision has to now be made. Do you want the device to switch to Wi-Fi very quickly, or a little later when it's sure that the signal is good? What is the right point? And these thresholdings are really where everything is going on. This is where the decisions are being made. So that's why the background of my interest in this is, a practical solution, and it's also blurring the borders, the line between the Wi-Fi and cellular access. I had one other question for you.
Mm-hmm.
Your solution has some sort of a CQI feedback, and you have packet merging and things like that. How much is the infrastructure involved? How much support for a good solution do you really need from a Wi-Fi access point and the cellular network? Because a cellular network, you'll probably never have good support, because cellular networks are not going to be interoperable with all the Wi-Fis out there, right? So can this be a device-only solution?
So
Support from the infrastructure.
So this depends on this actually depends on this part here. So the interface between a ENOB and a Wi-Fi access point. So there are the two different protocols, LWA and LWIP. And for example, for the case of LWIP, you would just send IP packets, and you wouldn't need to change anything for the Wi-Fi access point. However, you would still need to have the support by the LTE network, by the ENOB node that is aware of the access points, and that is aware of and that implements this additional interface here.
Okay, and these are standardized things that that could be easily implemented.
Yes.
Okay.
But thank you very much for your questions and for the insights that you gave on the use case. It's very valuable.
Yeah, thank you. The use case is something that can be tested out. very easily.
Yes.
Different networks. I think it was always a bit of a problem. How will devices decide when to switch, because they are typically doing this mutually exclusive mode where
Correct. Yeah.
the traffic can either go through LTE or cellular. The hybrid mode that was implemented in iOS is that both interfaces would be active, but iOS would handle certain services, such as push notifications, I think, and whatnot on the cellular, which is more widely available. It doesn't want to break those connections and things like that. Whereas Wi-Fi would be sort of coming in and out, depending on strength of a signal, and then some connections would be migrated. I'm not sure what the Android really does there, but there is a possibility on Android to turn on both of them. I don't know. I haven't looked at your bibliography. Have you looked at things that have already been done in tinkering with these mechanisms of using both interfaces at the same time?
No, I have not. But actually a good point.
Yeah, there's some works out there, especially when multipath. They're typically coming under either multipath or something like that.
Yeah, thank you very much for your feedback also.
Yeah, sure. Nice work. Thank you.
Okay, if there are no more questions, and I think we can switch to the next presenter.
Okay, thank you.
Thank you, Andreas. Hi.
Hi. I'm the next presenter.
Right. So you can share your screen whenever you're ready, and introduce yourself a bit if you want to do a small briefing, and yeah, wait for questions. Okay.
Okay.
Thank you.
Here is my PPT. Can you see it?
Yes, we can see it. Just if you want, turn the presentation mode, maybe.
Okay. 然后I will present Mr. Guo for this presentation.
Okay.
Here is my presentation of our recent work, maintaining training efficiency and accuracy for edge-assisted online federated learning with ABS. Federated learning is a machine learning setting where many clients collaboratively train a model under the orchestration of a central server, while keeping the training data decentralized. The clients may be user devices or even whole organizations. The server can be the service provider in the cloud. During the training, there may be data interaction between the user devices and the cloud. In this way, a machine learning model can be collaboratively trained. Parameter server is commonly used for federated learning. It divides the nodes into server and worker. In parameter server architecture, workers do not communicate with each other. During the training process, each worker calculates the gradients independently based on the local training data and pushes the gradients to the server to update the global parameters. New parameters will be generated after the aggregation stage on the server. Then worker will directly pull the new parameters from the server. Federated learning studies implicitly assume that the training data is collected offline, and each worker uses the local data for its training. However, in the real world, the data for user devices can be generated in a real-time manner, and the existing method has some problems tackling these issues. Firstly, the training data batch size can fluctuate. It means there can be a decrease in batch size, but the decrease of batch size can hurt the training process. Secondly, the existing method does not consider the heterogeneous computing speed of the workers. It can result in low utilization of the computing resource. Thirdly, there isn't a consideration of the utilization of the training data, but the improper batch size can decrease the utilization of the data. Training batch size is an important factor in the training process. We did a series of experiments with the ResNet 80 model and CIFAR 10 dataset on the image classification task. During the training, we used a fixed learning rate based on the stochastic gradient descent, and we show the impact of increased and decreased batch size during the training. We first show the impact of increased batch size. Case 1 has a fixed batch size of 32. Case 2 and Case 3 increased the batch size from 32 to 64 and 128 correspondingly. The results show that Case 1 has the highest training loss, and Case 3 has the lowest training loss. It means that increased batch size can accelerate the convergence on the training loss, and more improvement on the batch size can further accelerate the training. Here we show the experiments with the decrease of batch size. In Case 4, we use a fixed batch size of 128. In Case 5 and Case 6, we change the batch size from 128 to 64 and 32 after the inflection point. We can see that Case 6 has the lowest training loss, and Case 4 has the highest training loss. It means that the decrease of batch size can slow down the convergence of the training loss. Furthermore, in Case 4, after the inflection point, Case 4 achieves an increase in training loss. It means that extremely small batch size will have a serious negative effect. We show a demo of the training in the existing method. In this example, each of 3 workers has 4 training data, but the computing speed for worker A, B, and C is 3, 2, and 1. As a result, the low processing rate for worker C results in a global weighting for it. In ABS, we adopt a buffer mechanism. By using batch size for worker A, B, and C with 3, 2, and 1, and store the rest of the data in the buffer, we alleviate the drag caused by the slowest worker. In fact, we adaptively change the batch size, consider the processing rate, training model, and the training data generation speed. We adopt an adaptive batch size to fit the changeable data generation speed. To fit the different computing speed, we set different batch size upper bound for different workers. To improve the utilization of the training data on the training model, we adopt a lower bound for the training batch size. Specifically, the training consists of warm-up phase and processing phase. In the warm-up phase, there will generate an upper bound and a lower bound. For getting the lower bound, we train the machine learning model with different batch size on the training data with 1 iteration. The batch size with the best training result will be set as the lower bound. For getting the upper bound, we set an iteration duration at first. The iteration duration is the maximum training time that can be tolerated. In each worker, the maximum batch size which can be processed within this duration will be set as the upper bound. The processing phase will start after the warm-up phase. In each iteration, after receiving the start signal from the server, worker will count the amount of training data in the buffer. To alleviate the fluctuation of batch size in the long term, only C% of the counted data will be selected. A smaller C can result in shorter iteration duration, while a large C can reduce the iteration runs. After that, the selected batch size is further restricted within the upper bound and lower bound to generate the final batch size. And the upper bound and lower bound are determined during the warm-up phase. The extremely small batch size will have a serious negative effect on the training process. So we introduce the batch size bound update module. The final batch size will be compared with the lower bound. If the final batch size is larger than the lower bound consecutively for k iterations, the lower bound should be increased. We set our method on an image classification task. We use CIFAR10 dataset and the ResNet18 model. To simulate the data stream, we download a series of files from Cargo. It consists 36 files. In each file, there are a series of traffic counts. We use the traffic counts as the number of data received by the corresponding worker. Note that we do not use the original timestamp of the files. We read a row of the data every 0.06 seconds. We use two of the files to simulate the receiving speed of two workers. Furthermore, we assume there is no network congestion. In the training data selection module, we choose 1% of the data in each iteration. In the batch size bound update module, we improve the lower bound when the training batch size is higher than the lower bound for 120 iterations. We compare our method with federated averaging, and in the comparison algorithm, each worker's training batch size is the size of the data on it. We show the training loss and the testing accuracy during the training. Compared with federated averaging, ABS can have a faster convergence on training loss and higher test accuracy. Furthermore, ABS can achieve a more smooth convergence process. In this paper, we propose ABS to maintain training efficiency and performance for edge-assisted online federated learning. In the future, we will consider other factors including transmission delay, training data collection, and to improve our design. Here's my presentation. Thank you. Can you hear me? Sorry.
Yes, we can hear you.
Oh.
Yeah, let's wait for questions. Thank you for your presentation. Can you leave your slides on the screen so people may ask about them? Yes, that's better. Thank you. Okay, guys, it's time to close the session. So since there are no more questions, I'll finish the recording here. Thank you very much